1/10 Jetson version of the ADE containers. Jack, we good? Okay. Sure. Continue doing that. Good? Okay. Okay. So we went over the basic publisher and subscriber examples. I think for now we're just going to kind of leave the actions and services to some other time. The majority of what you'll be doing is with topics. So the actions and services, you may see examples of them in Autoware.auto, but they're not pervasive. We only use them in 1 or 2 places, so it's not a big deal. So the last part of the ROS2 thing that I wanted to go over is just some general best practices. Whenever possible, try and install packages for ROS from the ROS repositories. Don't go build stuff yourself, because there's no need in just needlessly expanding your workspace with a bunch of packages that you have to wait to build when you could just download them by for Ubuntu, for example, sudo apt install ROS packaging. So if you want a driver for something, for a piece of hardware, somebody's probably already written it. It's probably available in the repositories. Go look for it, and on wiki.ros.org, there's a list of every package that's in the repositories, so you can find out if it's been released or not.
But how do we know whether it's a FOXP or not?
So in the version of Ubuntu or Debian or whatever that you're using, when you install ROS, you install it for a specific version, and that links it to the repository with only packages for that version. Yep. The only caveat to that is on Ubuntu 2004, both Foxy and Galactic were targeted at Ubuntu 2004. So you can have a package that's available for both Foxy and Galactic. But every package starts with ROS-name of the release dash the name of the package.
Can't we have 2 different versions of ROS installed and just to source just what you're working on?
Yes, you can. So you can install both Foxy and Galactic on Ubuntu 2004, and then, when you start working, you tell it you want to source that version, and then you can work in that version. But it will only work in that terminal. So normally, if you're working on a system with just like one ROS installation, you want to set up a script in your bash RC so that it automatically sources the folder for that version of ROS. And so that way, every time you open a terminal, you've already got all the ROS stuff available to you. But if you've got 2 versions installed, you don't want to do that, because you may want to work in the other one, and you can't override what's already available in your environment in bash. So you have to just leave it undone and then source it manually every time you want to change. So as I said, someone has probably already written the node you're thinking of, so go search for it with ROS2 in front of it, and you'll probably find a GitHub package out there already with it. As far as language choice, C++, and this is true not only of the languages themselves, but also of the RCLs for the languages. C++ has more low-level features. You will tend to be able to go into how messages are created at the class level and get deep down into all the inheritance and stuff in C++. You cannot do that in the Python RCL API. But Python is much quicker to develop. The language is just easier to write large, complex things in. So, whichever one fits your use case, it doesn't really matter. They're both interoperable with ROS.
I see what you meant by Jack asking by each node.
Yeah. So as long as they have a common message structure, basically, when you define messages, you can create a ROS package which just has message definitions. And when you build that package, it builds C++ headers, it builds Python objects, it builds Rust objects, it builds C# objects, and it just does that automatically when the package gets built. So all of those languages have access to some representation of that message. So when they publish to DDS, DDS doesn't care that it came from a C++ node or a Python node. It just knows this is the data, this is the message structure. Pass it on to whoever's listening. All right. I'm sure there will be plenty more questions as we go along about ROS, but feel free if you happen to think of any. And then we'll go on to Autoware 101. Okay, little bit of background. I gave some of this in the talk this morning, but Autoware.ai was the first version. It was started in 2015 by a gentleman named Shinpei Kato at Nagoya University in Japan. He originally started at CMU and then moved to Nagoya University. Autoware.ai is hugely supported. It's got a big user base, 3,800 plus stars on GitHub, blah, blah, blah. And it has lots of international adoption, supports a bunch of vehicles. And there are Autoware courses offered in 5 different countries. Automotive OEMs are using it. And there are a lot of good things in Autoware.ai. Autoware.auto is the next revision of that. And the reason we kind of left Autoware.ai behind, so just to give you an idea of the status, Autoware.auto is still used by a lot of people, but the most recent release that we made of Autoware.ai is the last feature release that will be made. We are now in maintenance mode, which means we're only taking bug fixes for the next 2 years. And at the end of 2022, Autoware.ai will sunset and we won't support it anymore.
So Autoware.auto is a fork of it.
No, Autoware.auto is a complete rewrite from scratch in ROS2.
Okay.
Yeah.
Because Autoware.ai was on ROS1.
It was on ROS1, and it was also a bunch of PhD projects smashed into one. So it was not well structured. It didn't have clearly defined APIs. It, just grew organically with a bunch of nodes piling on top of each other. And the documentation wasn't there. The launch files that launched sensible stacks just didn't exist.
So ROS2 actually you wrote
It was, so Shinpei's, yeah. So Shinpei's students, Shinpei's PhD students at CMU started it. And then when he transferred to Nagoya University as a professor, PhD students there started adding more and more nodes to it. So that's how it started. Like no one person. Oh, Autoware.auto. Autoware.auto was started by Apex AI, and it was from a contract from Tier 4. So Tier 4 knew that ROS2 was something they needed to move to. And the major reason for that is DDS is a much better defined standard than anything that was in ROS1. And so they were targeting a lot of automotive OEMs and manufacturers. And if you're going to go into that market, you need to be as close to real time as possible and be able to be safety certified.
So Tier 4 then sit it from that stuff. Got something out of it.
They started building services around Autoware.auto, just like they have with Autoware.ai. So Tier 4 is a company that is also, Shinpei Kato is their CEO, and they sell services that surround Autoware products. So they have like a robo-taxi service that is based on Autoware.ai.
Apex AI service.
Apex AI was paid to write the core of Autoware.auto, and Apex AI started making services around Autoware.auto as well. But they actually have a fork of ROS2 that is already ISO 26262 certified. So ISO 26262 is what's called safety element out of context. It means you can prove essentially that this stack of software is functionally safe. And so they have a fork of ROS2 that is certified as functionally safe. And you can, it is API compatible with ROS2. So you can run ROS2 code on top of their hardware ports.
Were you initially with Apex?
No, I'm good friends with a lot of guys who work there, but I worked with autonomous stuff in the past, and then I moved to the foundation. Yeah. So I've been at Apex a few times, but I never worked there. So this is generally how the foundation works. Just a high-level overview. Like the board of directors, they oversee like the high-level objectives of the organization. This is also missing the strategic planning committee, which was a new committee formed a few months ago. A year ago, sorry. But it's out of date, I'm sorry. Anyway, the technical steering committee and the strategic planning committee both report to the board of directors. Those two committees are made up of representatives of the premium member organizations. So you get a voting seat on those two committees. And then the ODDs that we're going to target for development and any other technical projects come out of the technical steering committee. The strategic planning committee offers a list of ODDs that the TSC can choose from for like the next ODD. But then under the technical steering committee and the strategic planning committee, there are work groups, and the work groups are open to everyone. It's not just for members. And I think I mentioned this before, but on Autoware.org, there's a shared calendar, and that has all the call-in information for every work group that's part of the foundation. So if you want to join the software working group and figure out what's going on in development in Autoware, you can just jump on there at any time and like be a part of the conversation.
What's the compatibility with, say, AutoSAR?
So AutoSAR is more something that would be like, you would have to make ROS2 compatible with AutoSAR first, and then we would make AutoSAR compatible. Autoware.auto and Autoware.ai are not intentionally shooting for safety certification. We are intending these as reference implementations so that people can see what a self-driving stack could look like and use them as a starting point to build it. So we try and get kind of as close as possible to safety certification standards without actually trying to work.
I know the John over at
Yeah.
he's frustrated trying to get a conversation.
Yeah, AutoSAR is a big pain in the butt when it comes to getting certified.
You know the guy that it's a long story.
Yeah, okay. I believe you. Yeah. So Apex.os is ISO 26262 certified. It took them like 5 rounds of revisions to get the certification. AutoSAR, I think, is probably. So anyway, we do things like trying to make sure that we statically allocate memory every time we start up a process, which is a requirement for AutoSAR and for ISO 26262. We all of our types within the Autoware stack, we make sure that they are fixed size types, and then if we have different definitions for them in the future, it's really easy to change them on different systems. Yeah, so we try and get close, like follow the guidelines for most of that stuff, but not actually get certain. So this is a again, very outdated list of some of the member companies for the foundation. So we have premium members that you probably recognize, like ARM and NXP and Lenaro, LG, Calray, Velodyne, those guys.
I think we have about 60 members.
Yeah, well, I think we're somewhere around 60. So this is very out of date. So the the major 3 projects that Autoware has worked on or is working on is Autoware AI, excuse me, Autoware.auto, and Autoware.io. Autoware.io is kind of not incredibly well defined right now, but essentially it's supposed to be like an interface between Autoware software and vendor software. So like if you have a closed source driver, we make it so that you can connect it with Autoware.auto. But Autoware.auto is kind of what we're focusing on for this hackathon. So Autoware.auto in general is a framework for autonomous driving. As I said, it's a reference implementation. It is completely open source, and by that we mean the development process is also completely open source. We have all of our issues and merge requests available for anybody to look at. You will find other autonomous driving stacks that are open source in quotes. For example, the Baidu Apollo stack. When I say that they are open source in quotes, I mean they do 100% of their development behind closed doors and then dump the source code on GitHub. And they call that open source. So we do our best to make sure that all of our operations are available to everyone, and you can, it's a nonprofit. We try to make it open. And Autoware.auto is also in development. We are not at the point where we are at feature parity with Autoware AI. We do not have every function available that you would need to do full robotaxi. Right? But we're shooting for that, and we're doing it one ODD at a time so that we make sure we have logical increments of our software development, and it's not this huge jump that takes 6 years to develop the feature set, and then when we get to the end, it's so inflexible you can't do anything but one thing with it. Right?
I got a question, John.
Mm-hmm.
Will the ADP move to Autoware.auto?
autonomous runway.
Oh, whoops, oh, okay. I thought it was,
AI? No, it was the first. It was the first demo for the first ODB for Autoware.auto. Let's see. Yeah, so as I was saying, like our intent is to ease the transition to a safety critical framework. So I already said stuff about the tests in the earlier presentation, and we attempt to maintain a static memory footprint if we can. Dynamic memory allocation is number one target for safety critical. Bad things happen when you dynamically allocate. And what if you can't get the memory? So this is like the simplest architecture diagram you've probably ever seen. But if you ever see anybody's autonomous driving stack, this is at the base of it. Because these are all the functions you need to have an autonomous driving stack. You need to be able to sense the environment. You need to format that data in a way that the rest of the stack can understand it in perception. You need to have localization to figure out where you are. You need to be able to plan a path to get where you're going. And then you need to be able to control the vehicle. That's it. That's all there is, and those pieces exist in every single stack you'll ever see. Maybe mixed around a little bit, but that's the general idea. And so we've come up with an architecture to try and implement that in a way that is specific to the operational design domain that we're targeting. So in AVP, or Autonomous Valet Parking, let me get to that one. Usage, autonomous valet parking. So when we were doing autonomous valet parking, this was our entire architecture. Scroll down again. And a lot of this we ended up reusing for the ODD we're working on now. But this was all we had, and this was, why does it keep doing that? This was what we used to drive around the parking lot in San Jose. You take input from two LiDARs, front and rear. You transform each of those because when you're talking about sensor data, it comes in the frame of reference of that sensor, right? So you have to move that to a common frame that's common to the whole vehicle so that you can fuse it together. So for each of the LiDARs, we transform all the points and move them into the frame of reference of the car, and then we fuse it together with point cloud fusion. From there, that fused point cloud would go into, for perception, a ray ground filter, which would separate the ground points from the non-ground points. Then we would do Euclidean clustering, which would cluster each of those based on distance and movement and so on into groups. And then we would use those detected groups to try and plan around things. We would also use the fused point cloud through a downsampler, which would just reduce the number of points that are in the cloud, to try and match it with a pre-existing recorded point cloud, which was our Ndt localization. Once you were localized, the pose estimate from that localization would go into our global plane. And from a web interface, or from, well, so the cell phone app that CJ was using was basically just a web interface. And you press a button saying, I want you to go to the parking spot. And it would take that pose estimate from NDT and then the hand-coded coordinates for where the parking spot was and say, how do I get from this place to that place? And the way it would plan among all of the lanes and the other parking spots and stuff is using a Lanelet2 semantic map. So Lanelet2 has an API where you can say, this is my current geolocation, this is my goal geolocation. Now using the network that's defined in this roadmap, figure out all the segments I need to go through to get from A to B. And so that's basically what the global planner does. It gives you a list of segments that you need to drive through on the map. So it would make a request to our map provider for Lanelet2, get that back, parse it, figure out how to get through the map, and then pass that global route to our behavior planner. The behavior planner would then take in the posed estimate from NDT as well, but the behavior planner is meant to take each of those segments and figure out how to drive based on a set of waypoints along each one of those segments. So the behavior planner calls a set of sub-planners depending on what type each of those semantic segments is. So if it's a lane, for example, we would use the lane planner, which basically just creates a virtual center line on the lane and then sets a bunch of waypoints down. If, for example, we were trying to get off of a lane into a parking space, then we would call the parking plan. And it sets up a bounding box, which is the lane plus the parking space that you're trying to get into, and a set of virtual boundaries. And then it solves the problem of how do you create a path that moves into this space without hitting anything. Unfortunately, that was kind of the function that we had the most problems with. It was using a nonlinear problem solver, and the mathematics involved in that were beyond any of us except the guy who wrote it. And so we are probably not going to end up using that in the end. Plus, about half the time, it just failed to solve the problem. Like, it would get there and say, I can't find a solution. And that's because in order for nonlinear problem solvers, they are very good at what they do, but they require incredibly well-defined constraints to the problem you're trying to solve. And if you can't give it those incredibly well-defined constraints with the detail level that it needs, it's not going to be able to solve the problem.
Hey, Josh, out of this, how much is ROS2 navigation package versus reading all
All of it's handwritten for Autoware.auto. None of it's nav2. And the reason is, when we started writing this, nav2 in ROS2 was not up to the level where it is now. And so we just continued writing on what we already had. We have plans in the future to talk with Steve Nasinski, the guy who runs the nav2 work groups and stuff, to find out where the crossovers are and what we might be able to use from nav2. But for now, it's all handwritten code just for Autoware. So the behavior planner would call the subplanners, get waypoints from them, and then aggregate those waypoints into a full path of waypoints from beginning to end. And then it uses the pose estimate to figure out where we currently are along that list of waypoints. And then it passes a small look-ahead distance of waypoints to the vehicle controller. In this case, we were using an MPC controller. The MPC controller, this part is actually wrong. The MPC controller then sends a set of commands, not a trajectory, to the vehicle interface. And the behavior planner actually chooses what gear the vehicle should be in, so that passes that to the vehicle interface as well. And then those get turned into vehicle-specific commands for the drive-by-wire system or software that we're using on the car and get passed down to the car. So that is the entirety of what we use during the autonomous valet parking demonstration to be able to park in a spot and then return from the spot.
So the spot was
In this case, it was. So the web interface had a button on it, and that button would send a WebSockets command to ROS, and it had the lat long of the center of the parking spot, hard coded. Yeah. So, and the main reason is because the semantic map that we have is not incredibly well made. We had another company make it for us, and they just didn't have the time to refine it the way it should have been. And because of that, like, a lot of the boundaries of the parking spots were not quite right, and things didn't overlap quite right. And so you couldn't route properly to every parking spot. So we just chose one and said, this is the one we're going to shoot for in every test. So that is the architecture as it was defined for AVP. But we are redefining portions of that for cargo delivery, which is the operational design domain we're targeting right now, and as well as racing. But cargo delivery is what most of the community developers are working on, because that's the one with the most commercial opportunity. If we have a lot of member organizations, and instead of paying like cash for the member fee, they can do something called full-time engineering equivalent, and they can dedicate anywhere from 0.25 to 1.0 of a full engineer's time to working on Autoware.auto instead of paying their cash for their membership fee. And if you're one of those companies and you have a say as to what your developer works on, if it's going to be racing or it's going to be delivering cargo in an industrial environment, you're probably going to choose the latter because it makes more sense for your company, right? So the majority of our developers are working on this rather than racing. We mostly get racing contributions through groups like you guys and Robotics.
And then who coordinates all this develops? Maybe dozens.
Me. Me with the help of some people in the software working group. Yeah. And then in the racing stuff, there are different groups of people. So Johannes handles a bunch of the stuff on the F110th side and a little bit on IEC, and then Jack does some stuff on F110th and IEC, and so racing's kind of spread around quite a bit. But the cargo ODD, I do most of the organization for that. So we basically go through in our development process and come up with the new features that we need to add and how that's going to affect the architecture of each of the components of the big architecture. And so in this case, this is the intent for our new perception stack. So we would do a lot of the same stuff with LiDAR processing, but also do outlier removal and removal of points associated with the ego vehicle, so that we have a blank space where the vehicle is in the point cloud, so we don't try and detect ourselves. Then we fuse that just like we did before, do ground filtering just like we did before. We do clustering, and then beyond clustering, we now also do multi-object tracking, which is fusing the inputs not just from the LiDAR, but also from the camera and hopefully the radar in the near future. And then we also plan on doing prediction, so that we can have estimated paths.
So what exactly the radar adds that the LiDAR in this case? In this case, it's so short distance, right? So what's radar?
No, radar's up to 175 meters.
No, for your parking.
Oh, so for parking you didn't add anything.
Oh, yeah.
This one's for cargo. Yeah. We didn't. So literally, we didn't even use GPS in the parking demo. It was just LiDAR. Yeah, radar, it's got, every sensor has failure modes, and radar helps cover some of the failure modes of camera and LiDAR. So radar is able to see through things like snow and rain and fog, and cameras and LiDARs usually can't do that. So you get kind of a safety fallback, and then also radars are better at doing things like velocity and acceleration detection, because they use the Doppler effect to measure the movement of the object. It's part of the technology. This is how it works. And LiDARs don't do that. They're time of flight based, right?
And then those radars, is it 2D?
Yeah, in this case, it's a 2D plane. So the active radars, they use an antenna array, and it has vertical segments. And so each vertical segment can detect an object with a distance associated with it, but it can't do any vertical discrimination. So you get like a chunk, and there's some object in that chunk, right? And you can get a velocity of that object and acceleration of that object, but you can't tell how high off the ground it is. You just know it's out there in that little space.
And then if the objects are not moving, does it work really well?
Yeah, it still works if they're not moving. It doesn't work as well for cross-track movement. So if the object is moving toward you or away from you, it's very accurate. If it's moving through the radar array, it has a harder time detecting that unless it's moving pretty quickly. And then there are some radars like Smart Micro, which actually have a two-dimensional radar array. So they actually can discriminate in vertical and horizontal. But they're fairly new. Anyway. Yes, you can, because radars can bounce off the ground and you can get returns from the object in front. But doing that reliably is a lot harder than it sounds. Being able to actually know that the return you're getting in front of the car in front of you is another car and not just an errant return off of some object, that's really, really hard to do. You tend to, like if you had a radar in here and we're facing it out that way, you would get reflections like outside of the building and under the floor and stuff, because FM waves bounce around, right? They don't perfectly penetrate every surface. They don't reflect perfectly off every surface. So you have to do a lot of filtering. Anyway, that's the plan for the perception stack. We planned to put into place a radar tracker and camera classification, distortion correction, all that stuff for the perception stack. And then for the localization stack, the only major item that we're adding here is GNSS input. There we go. Actually, that's not true. We're also making the state estimator a lot more complex. So previously, we were just taking the output of our NDT pose matcher, and it was giving us a pose estimate, and it would say, this is where we think you are. And that for the AVP demo, we just trusted that that was true. Unfortunately, it's actually really, really hard to tell when NDT matching fails. That's a really hard philosophical problem to solve, or logical problem, however you want to look at it. Because you can say, like, I want to try and match X number of times, but what if it matches and that's not the actual location you're at? You have no way of telling that that's not the actual location because you got a match, right? And there can be some certainty associated with that match, but it's never going to be zero, so you can't know when it fails. So anyway, in order to help alleviate that, we are also now taking the GNSS data and using that for the initial guess for the NDT matcher, so that we have an estimate of where we're at to start with. And then we're also fusing that GNSS data with the output of the NDT matcher in an extended Kalman filter, which is our state estimator. And so we have covariance data associated with GNSS data, and we have a little bit of covariance associated with the NDT, and we can kind of weigh them differently based on what environment we're in. Get a better idea of where we're at. And then the other thing that we didn't really use, I'll talk about that later, about frames. So we'll get into that in a little bit. Control, we don't really need to go into much. We're not doing a whole lot in there. We're adding prediction, as I mentioned, for the perception side. And then on the planning side, I think we basically, yeah, we're going to have two separate planners that work differently than they did before. So our major problem that we had before was when you would get perception data and you would call the behavior planner and say, I need to have the behavior planner call the obstacle avoidance planner and say, where are the obstacles at? How do I get around them? And you're also calling a bunch of sub-planners to like conglomerate this huge list of waypoints. By the time you've called all those sub-planners and gotten the list of waypoints together and then passed a portion of it along to the controller, the objects have already moved. So the pipeline that we had was really not well suited for dynamic objects. Worked fine for static objects, but it was bad at dynamic. So for the new version, we have created a static path planner, which will call the docking planner, which is our replacement for the parking, and the lane planner, depending on the segments of the route we're talking about. And then that will pass it on to the behavior planner. And the behavior planner will do real-time obstacle avoidance on the subsection of the route that we're looking at ahead of us, rather than on the entire route. So we really don't care about objects outside of a certain distance anymore. Or if we do, their prediction paths are going to intersect this at some point, then we care about it. We also want the ability to do lane changes and choose which lane out of a set of lanes is our default lane, and do that sort of stuff. So that's all going to be handled by the behavior planner, and that will output a trajectory with the desired lane associated with it. That will move into the velocity planner, which will do real-time collision checking and modify the desired speed associated with the waypoints based on detected obstacles. And then we also do traffic light management if we happen to get that far. That's a stretch goal. And then that final trajectory goes out to the control. So none of this has really been implemented in Autoware.auto yet. It's just where we're going. All right, so that's the high level architecture stuff. Now let's go code server. And you can see what the Autoware.auto implementation actually looks like. All right, so Autoware.auto at its base looks like this. For the most part, you can probably ignore GitHooks, GitLab CI, and GitLab folders. Those are all stuff associated just with GitLab. It doesn't really matter that much except for CI. Docs is where we store all of our markdown documentation for the examples and for the usage information and that sort of thing. The package design files are stored within the packages themselves. So that if you make a change to the code and you make it an merge request, and we don't see changes in the design doc, you probably missed it. Tools is where we store all of our stuff like our Docker images and our rules for client complete and our coverage scripts and stuff like that. So you probably won't have to deal with tools much. And then source is where everything else lives.
Is the cargo ODD or is the recent one?
So this is everything, both. So Autoware is intended to cover all of the past and current ODDs in one code base. So this includes all the code that was written for AVP, plus extensions for cargo, plus extensions for racing. And we break it up into modular nodes so that you can combine the parts you want to make the stack you want. Yeah. So common is where we store common libraries that are used. Like we have a geography library and a geometry library and a set of libraries for covariance insertion and map utilities, LiDAR utilities, stuff like that. And this is generally where you'll want to look if you feel like, well, there should be a function for that already written. It's probably in common somewhere. Control is where all of our controllers live. So, excuse me, there's a set of controller common nodes, which are ROS nodes, but they are classes that are meant to be inherited. So, for example, pure pursuit and model predictive control, they're both controllers, which means they're going to share a lot of code. So it makes sense to have a set of controller common nodes that have all the common functions between those things, and then you can inherit from those. Motion common is where a bunch of our common motion functions are, like getting the distance between two 2D points, getting the distance between 3D points, doing figuring out where you are along an doing interpolation between 2 points, that kind of stuff. And then there's the actual controllers, MPC controller, pure pursuit, and trajectory follower, which we need to rename.
What's inside a trajectory follower?
It's actually a pure pursuit implementation of which does not do both lateral and longitudinal. It just does lateral.
Okay.
So pure pursuit actually does lateral and longitudinal. MPC also does latitudinal and longitudinal.
Should do that.
Huh?
Yeah. Okay, got it.
Drivers is where we store vehicle interfaces, because we consider those a driver to the drive-by-wire system, and specific sensor drivers that don't have an open source equivalent. So,
Josh, once we get this, and then if we have, for example, this SIG LiDAR, we just have to go to the SIG website.
Right.
Just bring it over there and try out something there and we'll build next time.
So, what was the list? What was on the best practices associated with that?
Well,
there you go. It's already been released in binary. You can get it from the repo. So all you have to do is sudo apt install ROS foxy sick something. I think it's 6scan2, I think is what it's called. So you don't have to pull down the code into here to build it from source.
Okay, so that's the low-level ROS driver.
Yes.
But in this case, they have like a payment interface. If someone did for my phone, then.
So if you, for example, if you were doing like your own drive-by-wire system, you're going to have a ROS2 driver, which directly interfaces with the hardware and turns that all into ROS messages, right? The vehicle interface is like Autoware's driver to your driver. It takes Autoware specific messages and then turns them into your drive-by-wire system messages, and vice versa.
And then can I do them like install, or should I then just get the source to here or what?
So for Autoware, we currently don't release any of our packages onto the ROS repo, so they're not available as like apt installs.
Yes, that's what I meant. So it is like F1 template. Where does it go?
The vehicle interface part would go in here, and it won't be released on the ROS build file. It'll just be in Autoware.auto. But the VESC driver will be released on the build farm because that is totally unassociated with Autoware.auto. It's just a driver they're talking about.
Yeah, anybody else would like to be.
Exactly. So that will be released on the build
And
farm, and you can see
hopefully
what.
clear that's the best ROS2 best driver that we did at SSD.
Mhm.
We'll clear it and be available to everybody.
I publish it. I make it that way. So the release process is kind of complicated, but essentially you tell ROS, this is the location of my Git repository. Next time you do a build run, go and build it from my repository and make Debian packages. And so their build farm builds everything that they've been submitted and then moves those Debian packages into a repository you can sudo apt install.
Then nobody can move the issues in there.
Nope.
So
There's almost no management as far as that's.
yeah, because that's the kind of jump, right? When some of them they go,
Yeah.
that's a malicious code in there, and then people say, and now it's inside the whole thing.
Yeah, that is a threat when using open source code in general.
So you have not as much friendly country that really wouldn't start that.
Or the University of Michigan.
Yeah.
Very large just code.
Yeah. Were you aware of that one? They made trivial commits to the Linux kernel, and they were all like little tiny fixes over a period of time. But when added together, they made a malicious I think it was a buffer overflow or code injection, something like that, in the kernel of Linux. Yeah, on purpose. And then they wrote a paper about it. And then the guys from that were maintaining the kernel are like, you're never submitting again, ever, to the kernel.
Wait, what was the paper? Was the paper just like, here's a cool thing we did?
No, yeah, well, it was trying to prove a point. It's like, look what you could do over time without people monitoring this from a higher level.
But the problem, they weren't even tracking. Like, so.
I missed that part.
Yeah, I mean, like, they didn't.
So once you lose control over that also.
Yeah, they didn't have it properly tested to protect against it. It's that mistake. And then they were kind of like, initially they were unprotected. So it's like,
Yeah, anyway. So yes, you can, if you release a ROS package to the ROS build farm, nobody at OSRF or anything like that checks your code to make sure that it's not malicious. It is based on a trust system, and that's just the way they've designed it. So if you want to guarantee that any code that you use in your autonomous system is safe and will not do anything unexpected or malicious, you better look at every single line of code that you're including.
Yeah, so this is not helping to avoid yourself or whatever.
So Autoware doesn't use a ton of code from the community at this point. Like everything that's in Autoware.auto.
But it will, right? It will.
Yeah, it will. It will.
That's over here, that's avoid here.
Yeah.
That's why Joe showed that whole one say we all develop on OS and see the feature that I could just put on top of it.
Yeah.
Some particular countries that live exposed there, and as soon as they really fix the United States, and then
Yeah, but
want to make a big mess, really popular.
But the community, the ROS community is active enough on using the packages that are released on the build farm in most cases that if somebody detected that there was something malicious being done in a package and it was being used somewhere, it would be reported almost immediately.
Yeah, if you get it there. And if it's not slipping with the fixes.
Yeah, which is why it's important in an autonomous system that you make sure that you know the source of what you're using. So there are well-known community repos and there are well-known developers in the ROS community. And if you are not familiar with the code base, you shouldn't use that package. You either write it yourself or you dig through every single line to make sure that nothing's going wrong. Like that's really the only way you can avoid it. You will see a couple of device drivers in here. Those will drop away. They will not be part of Autoware.auto in the future. They should be maintained separately. They just haven't always been. So like that. Velodyne and XSense, yeah. And the reason there's a separate Velodyne driver in here from the community supported one is because this one was written before the ROS2 version. The Velodyne driver was available on the ROS drivers GitHub. And This one is intentionally like fully static memory allocated and thread safe and a bunch of other stuff. There's a whole article from Apex AI on why they wrote this and how it is different from the community one. So that's drivers. Fusion, you probably never use. It's got a Hungarian assigner in it, if any of you know what that is, and I don't ever use it for anything. Launch is related to launch files that we were talking about before, and there's Autoware demos, which is where we have all of our launch files for our full like demonstration stacks, like AVP, for example, Autonomous Valley Parking. Doing examples with Ndt extended Kalman filter-based smoothing, getting some LiDAR bounding boxes, LiDAR tracks, localization, that sort of stuff. And then Autoware.auto launch is a bunch of common launch files which are just like a portion of the stack. So if you just want to run perception, or you just want to run localization, these are where those files are located. Localization is where everything related to localization is at. Common stuff, NDT, that sort of stuff. Right now, it's just pretty much NDT. Mapping is where you can get Lanelet 2 based nodes like the map provider, which loads it into ROS and makes it available as messages. Ndt Mapping, which allows you to drive around an area and it will use Ndt to match frame to frame and then build up a map over time. It's not incredibly accurate, but it does work. Ndt Mapping. I don't remember what point cloud mapping is. I think it's just parent classes for Ndt Mapping. Perception is where things like point cloud filters, outlier filters, ray ground filters, voxel grid, downsampling, segmentation for Euclidean clustering. Ground truth detections is something associated with the LGSVL simulator, turning ground truth data from that into messages that we understand. Stuff in segmentation for Euclidean clustering, went through that. Tracking is where the tracking node for perception is going to be. Tracking nodes, tracking test framework. There's going to be stuff in prediction. There's not really much there now. And then URDF. So URDF is a file format that allows you to define the frames in a vehicle. So a frame of reference for each of the sensors, where they are located relative to a common frame of reference, and then, ROS has a system called TF, which allows you to publish the transforms between each of those frames. URDF files you can load with a node called Robot State Publisher. You can load that into memory, and then it will automatically publish all the transforms for every one of the frames in the vehicle. So it makes doing that a lot easier instead of publishing them one by one by one by one, every node. So the URDF folder in here includes an example for our Lexus RX450H, and then an example URDF file. Yes. So you give the robot name. You can define materials if you want to for the visualization. And then you use links to define the frames. So Baselink is, in most vehicles for ROS, Baselink is the center of the rear axle. And so it's a common externally accessible reference point on the vehicle where you can use to measure the offsets to all of the other sensors. And this is also where you can define like a mesh file that describes the outside of the vehicle for visualization. Navbase is our center of gravity link. So it's not very easily measurable externally, but you can define where it is with relation to the externally measurable one, Baselink. So you define that as this link being a child of the other one, and these are the offsets in X, Y, Z, and roll pitch yaw. Same thing with the IMU, GNSS, front LiDAR, rear LiDAR, etc.
We need to create one for this one, or is it already?
Yes, we do need to create one for this. Now, the only problem we're going to have is that we have different configurations.
So that's separate.
Yeah.
Yeah.
Yeah, like this one, for example, look at the right height of that one compared to this one. So now, actually, the right height won't matter because it's not attached to the rigid body, so it's fine. But like the position of the LiDAR versus this one versus that one is slightly different.
But the F110 is a standard build, right? That's it.
There are going to be 2 standard builds and then 1 open class, which means you can do whatever. So we'll probably create a standard one for the low cost one, which is this yellow one over here.
Okay.
And then we'll probably create a standard one for this one, plus or minus the real sense. I'm not sure about that part.
But here is the, sorry, I just said
Yeah.
something. Here's the thing with Autoware.auto, we have ROS2. So whenever somebody comes up with hardware that enables ROS2, we can put it on the car.
Yeah.
That's I think the new stuff we have here, the cool part.
Yeah.
Whenever it has a ROS2 driver, we can enable it.
Oh, okay.
And for example, what you see here on the Jetson NX, we have the Jetson AGX Xavier, you can run it there. We have the Jetson TX2, we can run it there. So it's then all from the same family. So it enables a lot of hardware we can put on.
Yeah. Okay.
So we're about at the time where it's been I think 2 hours since we kind of started. So there's a fair amount more to go through as far as ROS is concerned. Like the 2 other main topics that I want to try and get to are frames and how frames need to be defined in order for a robot to work, and then all of the some of the commands that you can use to kind of navigate a live ROS system. Do you guys want to go through those, or do you want to try and get started hacking away at the car?
Sorry, say again.
So there are 2 other pieces of information, 2 other topics that I wanted to go over. One of them was frames of reference, and outside of the car, the frames of reference that you should define and are defined in Autoware. And then the other one is when you're running a live ROS system with like a launch file, how do you look up topics? How do you look up nodes? How do you find out if they're connected correctly? You know, navigating that stuff with command line tools.
Right. Maybe you can. I mean, who has ROS2 set up?
He did it on one of the cars.
Sorry.
I think we have like a Docker container.
Okay.
That uses ROS.
Yeah.
Yeah, I've got a, and also Autoware.auto, we base our development environment on a Docker, a couple of Docker.
I was only wondering if maybe like do a little bit of stuff in the car once we're able to actually like connect to it and maybe more appropriately understand the directions of like okay, here's how you actually like write the script properly.
Makes sense. Totally.
That sound like a good idea?
Yep. I'm down for that. So we have 1, 2, 3, 4, 5 vehicles. That one, the one in yellow, is completely a science experiment because we don't even know if Autoware will run on the Nano. But the other 4, it should run just fine. So I think we're gonna have to like split up and just kind of group around a car.
When we're running it, are you guys running native or are you pushing Docker?
So it has to be with Docker, unfortunately, because it's using ROS Foxy, which is 2004, and the image only supports 1804 for Jetson.
Okay.
So
we can do it. Literally just pull it.
you could, except there's some configuration steps you need to do on the car so that you can even SSH into it. So is this one good to go? Okay, cool. Okay, this one also is ready to go. Why don't, so what has been done to that one so far? Okay, as in it's got Jetson or the Jetson jetpack flashed on it.
I think it has a folder.
Yeah, I think it's even last. So I think it's another.
Okay. You have the image and a SD card reader, right?
Yeah.
Okay. Would you have an SD card reader?
Oh, yeah.
Okay. So that one's already been flashed. This one's already been flashed. Do you want to try the Nano?
Sure.
Okay. So if you want to go for the Nano, and then you want to work with him to flash that one, you guys can jump on either group, whichever you want. You want to play around with the Nano or watch him do the instructions for flashing for the NX.
Yeah, this one's already flashed. It's just an older version.
Yeah, I'd recommend upgrading to the newer version because especially the newer version of Docker is really important. So yeah, I'd recommend starting from that. Like you can run the original F110 stuff if you want to, but like it's not even necessary to install it for this part if you don't want to. So have you gone through the instructions that are on f110.org now, like the new version with NX?
So I don't think I've gotten the F110 containers version, but like yesterday we got the Docker class, and then I all the lost time. So like,
Okay.
right now, I think the Docker version is fine for now. Like I
Okay.
the Autoware website and then
Okay. Do you have that connected to the Wi-Fi? Okay. It's to UCSC robocards. And can you SSH to it? Okay. Let me send the instructions for the special Docker container that I made for that has the Jetson stuff on it, and Autoware and all the prerequisites and all that stuff. I'll put that in the Slack channel. I'm going to stop the presentation for now. Okay. Okay. I sent all the instructions to Jack yesterday, so. Okay. Do you have the user that's on there added to the Docker group so that you can run commands without sudo? Okay. Cut that out then. And you said you already have ADE installed?
yeah.
Okay. Skip that. Okay, so this is the git command for cloning this version of Autoware.auto. And then there's a special ADE command to get into the Jetson-based container for it. So you'll have to delete the Autoware.auto copy that you've got on there, and then just clone in this copy of it, and then run the special ADE command, and you'll be in the container for it. It's probably going to take 15 minutes or so to download. But yeah, should be good to go. And then for the Nano, you're probably going to want to start like from scratch with a fresh install from the instructions that are on the website. Yeah. The only change that you'll have to make to it is when you go to the NVIDIA developer website, you'll have to choose the Nano instead of that's the only difference.
All right, so I should just start with the demo setup.
No, you can skip the Pinhouse setup. You just need the yep, that's the right. Do you know what version of Jetpack you have on it? Okay. And then after that's built, okay, and then I also put the command to build Autoware.auto in there. It's a little bit different because there's a package that's shared between the VESC driver and a couple of the drivers that are in Autoware.auto, but the version that works with the VESC driver is not the same version that works with the drivers in Autoware.auto, so you have to skip those drivers in Autoware.auto in order for it to build. So this is a colcon build command, just skipping those drivers that don't work with the other version of that common package.
This is creating a new document.
Yes. Yeah.
Yeah.
What are the specs on that laptop?
Oh,
Or even approximately how old is it?
it's new. I
Okay.
bought it like a month or two ago.
Okay. Does it have a dedicated graphics card?
I think so. It's not video, but
Okay, never mind that.
Yeah.
That's fine. So you can install Autoware.auto if you want to, and you can get up a running environment and then like play around with the topics and stuff.
yeah.
You just won't be able to simulate it because the simulator requires a dedicated NVIDIA card.
Got it. Yeah. I tried seeing like try messing around with try to do like a neural network before and in the installation of various things I realized I don't have anything there.
Yeah, that's okay.
Okay, cool. So how do I get to the Autoware? How do I
So go to auto or GitLab.com/Autoware Foundation. Go to Autoware.auto.
Oh.
It's okay.
Um,
And then go on book it. Yeah, so you can click on the documentation link. That'll open up the new tab.
so you set up the password. Oh, it's on GitLab.
Yes, GitLab.
Okay.
So right click on that documentation link and then open a new tab.
They're trying to get start first. Sleep.
And you want to install it with
Yep.
okay. So once you got to the point of having this page complete,
Yeah.
let me know, and I'll give you a place where you can start up some examples.
Cool, great. Sounds good.
Yep.
You try to get into the
What would you like to work on, sir?
Whatever you want me to work.
How about the vehicle interface? Would you like to work on the vehicle interface?
That's my dream.
So the problem that we have right now.
How far did Chekhov come?
So the vehicle interface he wrote is mostly fine, but the VESC driver has a conflict with something that's in Autoware.auto.
With what exactly?
So the transport drivers that we're using, the serial driver, the version that the new VESC driver was written on is newer than the one that's publicly available in the repos.
Okay.
So, and then two of the drivers within Autoware.auto rely on the older one. So when you download it into Autoware.auto and then try and build, if you use the old one, the old drivers work fine and VESC doesn't. If you use the new one, VESC works fine and the other drivers don't. So what I did to get around that is I'm just having everyone colcon build and then skip the drivers that break.
Okay, that's fine.
Yeah, it works okay. So
So what did you test so far? Nothing, or like on the car, or
the car has the Docker container running on it, and the Autoware.auto stack is built in that container.
okay,
That is all as far as I've gotten.
okay.
So would you like to? What's the easiest way to do this?
To see what I can do,
Yeah.
what I really can do.
Yeah. So try. I would say take the code that he's written for the vehicle interface and make a merge request from that into the F110th fork of Autoware.auto.
Yeah. Let me first check out where did he put that to? On your GitLab or on our GitHub? Do you know that?
GitLab. Are you talking about the F110th fork of Autoware.auto? That's on gitlab.com/F110th-official.
GitLab.com/F110s.
F110th-official.
So which one?
F110th dash horizontal line.
This one? Yeah.
Yes, OFFICIAL.
Ah,
There we go.
Okay.
Okay, so that's the fork of Autoware.auto.
Yeah. You created for the F110 version.
Yeah. And then if you click on that,
Yeah.
Autoware.auto, not the documentation link, the actual name of the repo.
Yeah.
Go to the branches.
Mm-hmm.
So F110th dev is the primary branch for this repository. And then I created another one called F110th dev Jetson test, which is all the Jetson add-ons. So if you want to, I would say just make the merge request into F110th dev, and then I can rebase F110th dev Jetson stuff on that.
Okay. So from F110 dev to F1 dev Jetson test.
Yes, correct. So let me show you where the merge request is that he made to the official Autoware.auto.
Yeah.
So open up a new tab and go to gitlab.com/Autoware Foundation.
Question.
Yeah.
That's a Nano 2 gig.
Doesn't care.
Okay. We'll go with that.
What do you mean, the 4 gig RAM or?
Yeah.
That's a standard one. It's the
The image is for the developer. Download the image, just a Nano developer kit, just a Nano 2 gig.
Oh, I think it's the regular one.
yeah, it's a regular. It's not below one.
Okay. Then go to Autoware.auto, and then Autoware.auto again. I know.
We love this structure.
Go to the merge requests.
Yeah.
And just do a search for F110. Oh, not. Go back. Just hit back. I think it's in the first page.
Maybe not.
Maybe not.
Maybe second page or
Yeah, try it.
too much.
No. It shouldn't be that far back. How the hell is it?
Adding West driver interface.
Yeah, that's it. Desk. That's right. Desk, not
It's draft.
yeah. Yeah.
Okay.
So yeah, so click on that. And so this is his fork and his branch that he's requesting to merge into our master.
Mm-hmm.
So I would take the code that's on his Desk Autoware branch and then either make a merge request or just straight merge the code that's changed on there into the F110 dev.
Okay, but he wants to go into the master of Autoware.auto.
Yeah,
Yeah.
And the problem with that is the whole transport
Of course.
drivers thing. So it should be fine to merge it into the F110 version because I'm having everybody run a special Qualcomm build command.
Okay, but can I organize it from here, or do we have to set this up, like download and merge it again?
Do that.
Like,
do
I pull that and just create a new merge request for?
Yeah, so what I would do is I would pull down the F110 dev version,
Yeah,
then
push this stuff.
yes,
right?
yeah,
Right.
push this as a branch onto F110
Yeah.
whatever, and then make a merge request from that branch into F110 dev.
Yeah, I think that's the only reasonable way.
Yeah, that works. Cool.
Awesome, thank you.
Yep. Also, if for any reason you need an ARM instance to build stuff on, and you don't want it to take a day and a half, I spun up an Amazon EC2 instance that's ARM based, so we
Okay.
can build stuff there.
Yeah. That gave me a hard time with the drive page too.
Oh yeah, oh yeah.
That's
I hate that system.
yeah.
I helped.
It gave me gray hair.
Yeah, I helped NVIDIA write the instructions for flashing that system.
Oh my god. I mean, it like back in the days it was fine because it was one of the first, right?
Yeah, right.
So
Exactly.
I don't complain about
Yeah,
that.
exactly.
But you need a lot of patience.
But now you know why they don't support it anymore.
Is there something else coming up?
Yeah,
Because
the
this is here?
the AGX Xavier is what they recommend in place of that now.
The big one?
Yeah. Yeah.
Is there after the Pegasus? Like Graphics 2, Pegasus? Is there another?
Oh, maybe it's the Pegasus.
Pegasus right now is or AGX Pegasus. Right?
Yeah. That's what it is. AGX Pegasus. That's the successor to Drive.
Yeah,
PX2.
Yeah, and there's nothing else right now, right?
Correct. Nothing else.
Once I got it. You have an adapter?
Where'd Jack go?
You need like a full.
Yeah, because I have a full list.
I don't have an adapter for this.
How about I just transfer the image?
Okay, yeah, but
Well, so he's got a USB adapter with an micro SD slot.
Oh,
So if you've got a USB port, then it should work.
I think it's, okay, well, we got a little, yeah, this is.
Yeah. Sure. You need 5 adapters to get from one format to the other. There we go.
Dedicated graphics cards for this SPR simulator, right?
Yes.
So I can run a simulator and the graphics card is okay.
Say that again.
So I'm just trying to see whether I can run Autoware. I should install Autoware on my laptop. But my graphics card is dedicated. So I'm like, when do I try to run a simulator? If I can run that, then probably I should install Autoware.
You won't be able to, and the reason is that the version of the simulator that works correctly with Autoware.auto is a slightly older version, and it's only available as a Docker container. And the only way you can get access to a graphics card through a Docker container is with NVIDIA's container toolkit thing. So it only works with NVIDIA right now. Yeah. So you might be able to run the brand new version of the SVL simulator, but gear shifting won't work. Everything else will work, but not gear shifting. Yeah. So you can at least like run. So for example, like the AVP Autoware.auto AVP demo, you should be able to run everything in that except for the simulator, which means you'll get the whole stack running and you'll be able to visualize it in ARM. No, because there won't be any real sensor data coming.
So you can run it, but
Yeah, you can run it, but it won't go anywhere. Yeah.
the same.
In the perception demo, there's a ROS back in there, though, and you can play back the ROS back and do the rest of the perception. So that'll at least get you a stack running with some real data. Also, someone had asked earlier about the recording from this morning. I'm posting the link to it now on the ROS discourse post. So.
I think we're good.
Oh, yeah. So just to stop the recording, keep going.
Go ahead and stop it. I've actually stopped the Google Meet like 5 minutes ago.